All right, so first, anybody have any questions about the lab test? Yes?
What did you expect for the first one?
The first one.
Yeah, the first question.
Okay, so the two labs took slightly different tests, but I can give you the gist of it. So so it said, here's the one I'm going to do. It said 0 position on the ground.
Excuse me,
Okay.
looked at it, I meant the second one.
Oh, second one, okay. Well, people did it in all sorts of different formats, so whatever format you want to use is fine with me, but let me go through the thought process on this one, because actually I think this is a really important one. So I'm going to break it up into pieces like this. There's A, there's B, there's C,
Sorry, can I grab mine?
it is somewhere in there.
Sorry about that. I think I was going to be able to read it.
Did you maybe take it with a day class?
Nope.
No? Oh, there it
Oh,
is.
there it is.
Got like it.
Okay. Did you want me to step out while you review this? Since it's still going to take a minute.
Oh, that's a good idea. Would you mind doing that? You did great on this, Ted. Okay. Okay. Now, let's. Okay. So let's first go through the velocities. The velocities of the different regions all come from just the tangent to these curves, thinking about whether the slopes are positive or negative. These are all positive slopes all the way up until C. So we have a positive velocity from A all the way to C, and then a negative velocity on the other side. And now for the acceleration, we have to think about whether it's concave up or concave down. If it's concave up, is like a cup, that's positive acceleration. So it's concave up from A to B. Concave down from B all the way to D. And then concave up again from D to E. And then you can use that information to tell you where it's speeding up and slowing down. If the signs are the same, it's speeding up. If the signs are opposite, it's slowing down. So from A to B, it's speeding up. From B to C, it's slowing down. C to D, it's speeding up. And D to E, it's slowing down. Any other questions about that one? The opposite one? Yeah. So this time the velocity is negative all the way from A to C. And the velocity is positive from C to E. It's concave down from A to B. Concave up from B to D. And then concave down again from D to E. And so from A to B, basically since these graphs are the same shape, the only difference is what you've chosen as the positive direction. They have to be speeding up and slowing down at the same time. So this is still speeding up, slowing down, speeding up, slowing down. Any other questions about the test? All right. Yes.
Yeah, I had a question about the second problem.
Mm-hmm.
Number 7, and the question.
On the lab test or on the homework?
No.
Okay, great. Let me just. Okay. So number 7. That's in the friction problems. Does anyone have that in front of them? Do you have it with you?
No.
Anybody?
It was the one labeled N2L.
Oh, yeah, okay. So number 7, N2L, that's the tension one. You want me to go through it, or do you have a specific question about it?
So, yeah, if you could go through it.
Sure. So that's the one where you have a bunch of pulleys, you have a mass, let's see, pulley, 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 and then it's all connected sort of like this. And the mass is 150 kilograms. And we want to calculate the two force vectors applied to the mass by the cable. So this problem is one where you look at it and it's easy for your brain to sort of overload because there's just a ton going on. And if you can just start the process of like, okay, I'm going to just draw this, I'm going to choose something to isolate, draw the outline, think about the rules for forces from the things we've talked about, it simplifies a lot. So a free body diagram of that mass looks like this. So we're isolating the 150 kilogram mass. There's a weight force. 150 times 9.81 is 1471.5. And now we go around the boundary of the body looking for contact with the outside world. And there's only two places where the outside world contacts the boundary. That's where the cable touches, on the left and the right. And so for the cable thing, I said, you don't have to do this, but I like to include a little stump of cable in what I'm isolating. So it's like that. And then the force applied by the cable goes right out of the stump, parallel to the cable. We don't know the magnitude of this tension, but we do know that it's the same cable in both of these two places. And if it's the same cable, the magnitude of this force has to be the same for both of these. We're eventually going to need to use these angles, which makes me wish I would have drawn this better. But this is 40 degrees, and this is 40 degrees. Any questions on the free body diagram? So this is one of those where probably most of the work in this problem is just getting the free body diagram right. Once you're here, things sort of fall into place. You just have to get the angles right now. So Newton's second law says 0, negative 1471.5 plus, to get from the positive x-axis to this is a 40-degree angle. So you have t times the cosine of 40 and the sine of 40. And that is 0.766t, 0.643t.
Can you repeat that again?
Yeah, so for this one, this angle's 40 degrees. And so if you put the tail of that at the origin of the coordinate system, your angle theta is 40 degrees. And so this force vector, it has a magnitude of t, is t times the cosine of 40, t times the sine of 40. And then for the other one, it's this way, and this angle is 40. So if you put the tail at the origin, now the angle you want is from the positive x-axis, 180 minus 40. So theta is equal to 140 degrees. So the vector is t times cosine and sine of 140 degrees, and that is negative 0.766t, positive 0.643t. And that's all the forces. And so that's equal to the mass of the chosen body times the acceleration. It says that this mass is hanging there, so it's not accelerating. So we just have a mass of 150 times an acceleration vector of 0. And that gives us two equations. The x equation says 0 plus these two things that cancel. Well, I'll write it out. So 0.766t minus 0.766t is equal to 0. Those cancel, and so you get the equation 0 equals 0, which doesn't give us any information. And then the y equation says negative 1471.5 plus 0.643t plus 0.643t is equal to 0, or 1.286t is equal to 1471.5. And so what do you get for t?
1144.25.
What is it?
1144.25.
1144.25 newtons. So that's the magnitude of that cable force. That's the tension in the cable. But this problem asked for the force vectors applied by those cables, which means we're going to plug the value for t in once to this and once to this. So the left force says 1144.25 times negative 0.643 is the x component, and the y component is 1144.25 times positive 0.7, what did I say, 66? And what do you get for those? The left. It should be the other way around. You're right. Oh, yes. I did it backwards. So this one should be 0.766, and this one should be 0.643. Okay, so sorry, what's...
The left is negative 876.5.
876.5, okay.
735.5.
735.5. And then the right force is 1144.25 times positive 0.766 and 1144.25 times positive 0.643. The magnitudes are the magnitudes stay the same. We just get a different sign for the x component. So this is positive 876.5, positive 735.5. And those are in newtons. Any other questions about that one? I like that one because it looks crazy, and then if you start following the rules, all the craziness disappears from the problem. Any other homework questions? No. No. You just have to try to remember it. No other questions? Okay, now you. Yeah. On the friction ones?
Yeah. Remember when there was a question as to why the friction was the same way on the answer.
Okay. Oy, 11. Okay. So this is another one where you look at it, start thinking about the forces going on, and you can sort of get overloaded. The only way to do it is just is just think one by one about what's touching what are the rules for that kind of force. So this is the one where you have a 10 kilogram box sitting on top of a 25 kilogram box. And they're connected to each other by a cable that goes over a pulley. And at the instant shown, the top block is sliding to the left. So this has a velocity that way. This one has a velocity that way. The coefficient of kinetic friction between the blocks is 0.1, and the coefficient of kinetic friction between the bottom box and the floor is 0.2. And we want to calculate the acceleration vector of the 10 kilogram block. Okay, so there's no reason to pick one of these over the other one and what to isolate. It turns out we're going to have to isolate both of them. I'm just going to start with the top one. There's a weight force of 98.1. There's a contact force pushing up from the 25 kilogram box. I'll call that N1. We're going to have a bunch of these normal forces in this problem. There's a friction force opposite the direction of motion. So that is 0.1 times N1. And then there's a cable force in this direction, T. And then if you keep going around the boundary, there's nowhere else where the outside world, outside of what we've isolated, touches the boundary, so that's it. Newton's second law, at least the good news with this problem is all the directions are easy. We don't have to use cosine and sine for anything. So T is in the positive x direction. The friction force is in the positive x direction. The normal force is in the positive y direction, like always. The weight is in the negative y direction. Question? And then all that's equal to the mass times the acceleration vector. So we get one equation that says T plus 0.1 N1 is equal to 10A. We get a second equation that says N1 minus 98.1 is equal to 0. I'm just going to write that as N1 is equal to 98.1. And if we combine these two, sorry, let me write this differently. So let me write this as equation x and equation y. So we use equation y to calculate N1, plug that into x, and we get two equations out of that. T minus 10a is equal to negative 9.81. I did a couple of algebra steps there, but so stop me if there's a problem with that. We have a second equation that says N1 is equal to 98.1. And that's the information that we have coming out of isolating that first body. And now we'll isolate the 25 kilogram. Okay, so there's a weight, 25 times 9.81. That is 245.25, I think. Then there's a pushing contact from the floor to the 25, so I'll call that N2. Yes?
So is equation 1 equal to negative 9.81 or negative 98?
It's 0.1 times 9.81 and then moved over to the other side. I did like a whole bunch of algebra without showing it. Okay, so now what direction is the friction force acting from the ground to the 25? It's in the negative x. So it's this way with a magnitude of 0.2 times N2.
Would that matter if we put that on like the right side of the left?
Nope, it doesn't matter where you put it. Although I suppose things with a lot of forces, it can make it easier to figure out what you mean, what each force is representing if you sort of put it roughly where it is applied, you know. Then we get to that friction force, the cable force, the tension force. It acts in this direction, and it's the same cable, so it still has that magnitude T. Then we get up to the top, and the forces at the top are, we can just think about those in terms of Newton's third law. This N1 and this friction force were contact forces between the 10 and the 25 applied to the 10. So if we want those contact forces, those same contact forces applied to the 25, we use the same values and just switch the directions. So we have N1 acting this way, and the friction force acting this way. And, oh, we know what those are. So I can just fill these in numerically. So this is 98.1. The friction force is 0.1 times 98.1, so this is 9.81. Is there anyone who still has any idea what I'm doing? No? Just Ray?
I was confused as to, the second friction, why it was going in that direction.
Okay.
Maybe I was
Yeah. Yeah.
overthinking the box going the other way.
You were when you were doing it, or now? Does it make sense, or?
No.
It still doesn't. Yeah, yeah. Okay. Well, these two things here are the force vector on the 10 by the 25. And so if you want the force on the 25 by the 10,
I thought the friction was going the other way.
okay, so let me try to explain it this way, and then I can answer that if this is still confusing. But so the n and the 0.1 n together, those are the force vector on the 10 by the 25. What Newton's third law says is to go from the force on the 10 by the 25 to the force on the 25 by the 10. You keep all the magnitudes the same and change the directions. So I'm just changing. So we still have the magnitude n1 here. We still have the magnitude 0.1 n1 here, but the directions are just opposite what they were.
That's a force. I'm just confused on, like, wouldn't the direction of friction be going the other way? I'm just confused why the 9.81 is, that arrow's going to the left.
The 25 relative to the 10 is sliding to the right, and so the friction has to be to the left.
Go down. Okay, gotcha.
Any other questions about that Newton's third law part?
Could you just say that again?
Yes. Yeah, the whole thing about Newton's third law. So the force that is applied to the 10 by the 25 is that normal force and that friction force. That's the force that is applied to the 10 by the 25. And so if you want to represent the force on the 25 by the 10, Newton's third law says it's exactly the same magnitude but the opposite direction. So I'm going to take both of these two things, keep the magnitudes the same, and just switch the directions. So N1 now is, when I go to the 25 kilogram, N1 is now facing down instead of up. And 0.1 N1 is now facing to the left instead of the right. So that's Newton's third law. Yep.
So you reverse it on the top one, you reverse it on the bottom one as well?
I only reversed it to go to the, I didn't reverse it on the top one.
Okay.
So this is what it is on the top one.
Yep.
And then when I went to the bottom one, since now we're talking about, so for the first one we're talking about the force on the top by the bottom.
Yep.
So now when we go to the bottom one, we're talking about the force on the bottom one by the top. And to do that, we keep the magnitudes the same and switch the directions. And if you go back to your notes on Newton's third law, you'll see that wording in there.
No, that makes sense.
But there's no doubt that that step is the trickiest step in this problem. So now representing it isn't as bad as, like, this is one where the free body, doing the free body diagrams right is the whole problem, you know. So Newton's second law says, so the 9.81 is in the negative x direction. The 98.1 is in the negative y direction. T is in the positive x direction. The weight is in the negative y direction. N2 is in the positive y. Point 2 N2 is in the negative x. And then you think you're out of the woods, but there's one more little trick. And that is representing the acceleration of the bottom one. Okay, so the mass times the acceleration. Well, these two things are connected by a cable. So if the top box moves an inch to the left, what does the bottom box do? An inch to the right. And so if we're representing the acceleration of the top box as a0, we have to represent the acceleration of the bottom box as negative a0. And we're trying to calculate the acceleration. So let's see. The y equation says negative 98.1 minus 245.25 plus n2 is equal to 0. So n2 is, who knows, 343.35. And then plug that into the x equation, negative 9.81 plus t minus 0.2 times 343.35 is equal to negative 25a. Can someone tell me what, well, let's see. So I'm going to rearrange this like t plus 25a is equal to 9.81 plus 0.2 times 343.35. Positive 78.48. Okay, so now we have this. And we have this. And we can, that's a system of two equations for two variables. We can, okay, so I'm going to call, so I'll call this one star. I'll call this one double star. And then I'll go star minus double star. The t's go away. You get 35a is equal to I was just trying to get, so you can solve it by substitution and not worry about any of that stuff. I'm just trying to do it in a way that I can do it right here in front of everybody under the hot lights.
Can you scroll down a little? Which one is star?
So I think you get that, and then what's 68.067, not 68. I subtracted this whole equation. Oh, but this should have gotten bigger, I think. 70. 88.29. Negative? Okay. Oh.
You're subtracting a positive from a negative.
You're subtracting it.
Yeah, so it is negative.
Yeah.
Okay. So what do you get for A?
2.5.
And so that says that, so the acceleration of 10 is negative 2.520.
Or negative as well, because negative 10 minus 25. Negative 10.
Oh, yeah.
So then it's just all.
Everything's negative. Okay, so that says that the acceleration of the 10 is in the positive x direction. The velocity is in the negative x direction. So is this system speeding up or slowing down? Anybody have any other guesses? No, so the... well, actually, they're both slowing down. Everything's slowing down because the velocity is in the negative x. The acceleration is in the positive x. So that's slowing down. And then for the 25, it's the opposite. That one is frickin' hard. There's no doubt about that. I don't know.
Why would you do that?
I know. Well, so the answer is, when I made that problem, it was several years ago, so it was by accident. But the real question is, why have I continued to give that problem over the years? That I don't have an answer to. I probably just forgot about it before I got back to my office each time. I don't know. I'd say think of that as, there's not going to be anything like that on the test. You can think of that as like a challenge problem, help you sort of straighten out some of your ideas about that stuff, but I'm not going to do anything like that on the test. Any other homework questions? Okay. Okay, so the next topic is circular motion. And we've already done most of the stuff that we need to do circular motion. There's really just one calculation that, one easy calculation that I'm going to add to what you know. An object in circular motion is always turning. So it has a part of the acceleration that's perpendicular to the velocity. And it's sometimes speeding up or slowing down. So it sometimes has a part of the acceleration that's parallel to the velocity. In circular motion, a parallel, actually let me do perpendicular first since that's the one that keeps coming up. A perpendicular is called the centripetal acceleration. In other words, acceleration toward the center of the circle. And the parallel part of the acceleration is called the tangential acceleration. Well, that makes sense because we know that the velocity is tangent to the path, and so this makes sense with everything we know about the parallel part of the acceleration. So let me give a couple of examples. So first, circular motion without speed change. Well, we talked about something like this in the last lab. On the test, there was a problem like this. So if you have an object moving around a circular path like this, the velocity is this way. There's no parallel part of the velocity. The perpendicular part of the acceleration is that way. And so the total acceleration is toward the center. Toward the center of the circular path. Then if you have circular motion with a speed change, so let's say an object's moving around that path, and it's going this way, and let's say it's slowing down. The velocity vector looks like this. The parallel part of the acceleration looks like that. The perpendicular part goes towards the center. That's the centripetal acceleration. And the total acceleration looks like that.
That's kind of what we were doing in lab last week.
Yes, just like what we've been doing in lab. And so now the total acceleration points away from the center of the circle. I mean, not, total acceleration doesn't point towards the center of the circle. All right, so we're going to break circular motion up into these two types of motions. The first one is called uniform circular motion. That's circular motion without speed change. Or in other words, the speed is uniform. You know, that's where that name comes from. An example of uniform circular motion is like any kind of tetherball problem where you're swinging an object around a circle that's parallel to the ground. And the second category is called non-uniform circular motion. That's circular motion with a speed change. An example of that, have you ever watched men's gymnastics? It's awesome. So this is supposed to be a guy in a high bar. Okay, and if you you can't really see this on TV that well, but when you're right next to these guys doing it, because I used to be, because when I was a kid, I was like the worst gymnast in the history of gymnastics. But I would sit under here, and the guys on the U of M team would be doing this stuff, and you could hear the wind rippling their pants as they came through the bottom. Like as they got lower, they're speeding up, speeding up, speeding up. They go blasting through the bottom and then slow down as they go up, and they just barely go over a handstand at the top, and then non-uniform, changing speeds as it goes. Or if you ever watch like the guys at the circus on the motorcycles. It's hard to draw this upside down. They go slow at the top and fast at the bottom too. Okay, so I am going to give a set of steps that's going to work with every circular motion problem. And then we're going to start with uniform problems and then go to non-uniform problems. So first, a general method for all circular motion problems. Okay, so the first step that we're always going to do is we're always going to choose. So all the problems we do are in a plane. Okay, we only do two-dimensional problems. Real problems happen in 3D. So you kind of have to choose the two dimensions that you're going to use to view this problem. We're going to choose a view and a coordinate system. where the motion is visible as a circle. So let me give you an example. If you're doing so if you're talking about the motion of a car moving around a track, like a little, let's say like a little toy car. You want to choose a top view so that in your view, the motion of the car looks like a circle. Okay, like if you choose can you imagine if you chose a view where you're lying on the ground looking at this from the side, all you would see is the car going back and forth along a line? That's not a circle, so you don't choose that view of the problem. Any questions about that to try to clarify that, understand what I mean? Second, choose a point on the path to analyze. And when I say a point, I'm talking about a single instant where the object is at a single location. So if now this is your circular path and you've chosen a coordinate system like this, let's say that the point you choose to analyze is down here at the bottom of the circle. Third, draw a vector from the chosen point on the path toward the center of the circle. That's the centripetal acceleration. Also the perpendicular part of the acceleration, the way we've been talking about it. So that's the centripetal acceleration. And it has a magnitude of capital V squared over R, where capital V is the object's speed, and R is the radius of the circle. For if it's non-uniform circular motion, calculate the tangential acceleration, A tangent, Almost done. And then 5, the total acceleration is always equal to the centripetal plus the tangential. Six, draw a free body diagram. And 7, use Newton's second law. So that's what we're going to do just over and over again with these problems. There's one thing that's going to be new that we haven't dealt with before. And it has to do with, we've never really had to think about what viewpoint of the problem we were going to take before. It's always been pretty much given to us. Now we have to choose a view where the motion is a circle. One new thing. So now that we're choosing the viewpoint with which to look at this problem, there are going to be times when certain forces that we know are acting don't appear in our problem because they're acting out of the plane. If you choose a viewpoint so like for example, if like in that car example, we're going to choose a viewpoint where we're looking at the circular motion from the top. Then when we do a free body diagram of the car, the weight is acting like into the page from the way that we're looking at it. And so it's not going to come up in the equations at all, and we can just leave it out. And so that's something to look for. That kind of thing is going to come up. It's usually going to be weight and normal forces. So weight and normal forces will sometimes act out of our chosen plane. And then won't appear in our equations. There's one other thing about this. So this general method is what we're going to follow for every kind of circular motion except one. And, you might think that means that the one that isn't going to follow this must be some kind of really special motion. It's not really. It's just there's one thing that's a little easier if you view it from a different angle. So this is going to be valid for all circular motion except tetherball problems. And so I'll talk about how to deal with those separately. We'll just, so you'll look at problems, you'll say, like, is this a tetherball problem where you have a ball hanging from a string spinning in a horizontal motion? If it is that, we'll have a method for that. If it isn't, we'll do this. Okay, before I go on to an example problem, let's talk about this centripetal acceleration. The magnitude of the centripetal acceleration is always equal to the speed squared over the radius. So I just want to point out that makes sense intuitively. So does that make sense? So think about like taking turns in a car. The acceleration is how much you crash into the person sitting next to you in the back seat. Okay? That's the acceleration. So first, is the acceleration greater or less as the speed increases? Okay, so imagine taking the same turn. So you're in the back seat with someone that it feels awkward to touch, and so you're trying not to crash into the person. And you take this same turn at two different speeds. Is it harder to avoid falling into them going slow or fast? Fast. So faster means greater acceleration. So speed should be in the numerator. Okay, so this thinking doesn't tell us that speed is squared, but it does tell us that that v should be in the top of that fraction. Okay? And now second is the acceleration greater or less as the turning radius decreases. So as you make that turn, say you keep going the same speed, but you make that turn in a smaller and smaller place, smaller and smaller space, does decreasing that turning radius make you bump into that your boss more or less? More. So smaller turning radius leads to increased acceleration. So R should be in the denominator. Okay, so just thinking about our experience with circular accelerations, you can tell that the expression for centripetal acceleration should have speed in the numerator, R in the denominator. You don't know anything about the powers or whatever. That just is something that you have to take my word for. But you can sort of make sense out of this, you know. Any questions about that? All right, well, let's stop there, and I'll do a couple problems next time. If we still have a country. Yes.